Hello, and welcome to lecture number 5 of College Mathematics for Business. This is Math 208 at UWM. Anyways, today we're going to cover the inverse of a square matrix. So we've got a couple of goals for today. We're going to start with describing, understanding, and determining the identity matrix. Understand a multiplicative inverse and recognize that m times m inverse is equal to I. We're going to do the basic properties of a determinant and find the determinant for 2 by 2 matrices. And then we're going to find the inverse of a matrix using both Cramer's rule and by Gauss-Jordan. So let's get started. The inverse of a square matrix. Thus far, we've learned what a matrix is, how to add and subtract it, multiply it by other matrices, or by scalars. We add a few more concepts, and we can almost work with matrices as we do with other algebraic elements. And that's really what our goal is, so that we can, in fact, begin to approach a subject that's called linear algebra. It's a large branch of mathematics, and it's devoted to the study of using matrices, etc., in an algebraic fashion. So I'm going to turn off my, there we go, and let's go. So an identity matrix. What is an identity matrix? Basically, an identity matrix is 1. So it's similar to 1 that we would typically see in regular algebra. In this case, it's a square matrix with 1s on the diagonal and 0s everywhere else. So we can write it, and these are just different ways of writing it. We can write it as in, we can fill in everything, or we can just write 1s down the diagonal. Each one of those represents the identity matrix. Now, in regular math or regular algebra, anytime we multiply a number by 1, it equals the original number. The same thing is true for matrices, so that whenever we multiply any matrix by the identity matrix, we end up with the original matrix. And A times I is equal to A, and also I times A is equal to A. So this operation is commutative. Now, if you recall, usually when we're multiplying matrices together, we can't say that they are commutative. You can't change the order. However, when we're dealing with the identity matrix, you can, in fact, do that. I'm going to just actually multiply these next two examples out. So find AI and AB using matrix products rules. So what we have is we have a 2 by 2 matrix and a 2 by 2 matrix. So the inners are the same, so we know that we can get it, and that it is a defined action, and we know that the output is going to be a 2 by 2 matrix. So let's begin. And it's the row times the column, so we have 5 times plus 0. The next one is 5 times 0. So let's actually write that in. So here we have 0 plus 6. The second row times the first column is 7 plus 0. Second row, second column is 0 plus 8. And that equals 5, 6, 7, 8, which is our original matrix. So A times I, or matrix times I, is equal to that matrix. Now let's try it in the other order. We have a 3 by 3 matrix and a 3 by 3 matrix. We know we can perform the operation, and we know the output is going to be a 3 by 3 matrix. So we take the first row, first column. So it's 3 plus 0 plus 0. Okay, first row, second column is 2 plus 0 plus 0. Third column, first row, third column, 1 plus 0 plus 0. Now let's go down to the second row, first column. 0 plus 1 plus 0. 0 plus 2 plus 0, 0 plus 3 plus 0. Let's go to the third row, first column, and we'll start to get a little bit faster. 0, 0, 2, 0, 0, 3, 0, 0, 1. And now if we compare this, you'll notice that this is the exact same as our starting matrix that we multiplied by the identity matrix. It's just a way of verifying that it does in fact equal that. And we'll be doing some tricks like this again a little bit later. Generally speaking, when you're working with the identity matrix, you're not going to have to do this multiplication. If it asks you specifically to do that in a problem, then do it. But otherwise, you can just say, yes, I know that the identity matrix times the matrix is that matrix. Let's take a look at multiplicative inverse. The tongue twister, right? Anyways, any number multiplied by its multiplicative inverse is equal to 1. What does that mean? We're typically going to use the multiplicative inverse, not the additive inverse. But for rational numbers, the numbers that you're typically working with, fractions, etc., 2 times 1/2 is equal to 1. Or another way to say that is 2 times 2 to the minus 1 is equal to 1. So 1/2 is the inverse of 2, and the inverse of 1/2 is 2. So these are inverses of each other. 2 and 2 to the minus 1 are inverses of each other. The same thing is true if we're talking about 98. So the multiplicative inverse of 98 is 1 divided by 98. In algebra, that's 1 divided by 98 is the same as 98 to the minus 1. So those are the multiplicative inverses of each other. So it sounds like a complicated phrase. It's not really that complicated. Now, generally speaking, in real numbers, everything has an inverse. That's not true for matrices. Not all matrices have an inverse. So first of all, we're going to be talking about square matrices when we talk about inverse. And not all matrices have an inverse. If an inverse does not have a matrix, we call it singular. So a singular matrix does not have an inverse. If a matrix has an inverse, so if, for example, the matrix A has an inverse, we designated that by a to the minus 1. And we say that a to the minus 1 equals I. Again, this is commutative, so you can change the order of the multiplication here. How do we find the inverse of a matrix? Well, there's a couple of different methods we have to find the inverse of a matrix. Basically, there's two methods. If you have a 2 by 2 matrix, you can use a thing called Cramer's rule. And that requires knowing the determinant of a matrix. And we'll talk about that in just a moment. But that's generally only good for matrices up to 2 by 2. There is a rule for 3 by 3, but most people don't use it. So it generally applies only to 2 by 2 matrices. So Cramer's rule you can use for a 2 by 2 matrix. On the other hand, for any size matrix, we can use the Gauss-Jordan method. The Gauss-Jordan method that we learned the other day. So yes, there are applications to the Gauss-Jordan method. Again, we're going to augment our matrix in order to do this, but it's going to be a different augmentation than what we used previously. I'm going to cover the determinant of a matrix. I'll cover the determinant of a matrix and then go on to We'll cover the rest of it before I do some examples. So the determinant of a square matrix. What is that? The determinant of a square matrix is a single number. It gives you some information about it. We're not going to talk too much about the determinant, but this is except for what we're using it to find the inverse. But the determinant of a matrix is 0 when it has no inverse. When the matrix is singular, the determinant is 0. You can calculate a determinant for any square matrix, but in this class we're going to limit that to a 2 by 2 matrix. And there's a formula for it. So given a matrix M, the determinant is A times D minus B times C. Minus B times C. It's a relatively straightforward formula. You should be able to remember it. And then recall that for a singular matrix, the determinant is equal to 0.